Hi, my name is Jesse Rice, and I'm going to be talking about mast and hub interfaces. But before I dive into that, I wanted to cover some background, give an idea of what I'm talking about, and kind of what inspired me to pursue this as a project. So, this is an V-22 Osprey. It's a virtual takeoff and landing aircraft, VTOL. It takes off like a helicopter and flies like an airplane. It can also do rolling takeoffs, so it can kind of similarly take off like an airplane, with the caveat of it can't be in this orientation, right? The blades would hit the ground. So the nacelles are usually like at like 70 something degrees when it does that. So this is a nacelle. It connects to your prop rotor, which connects to your blades, and that's what spins everything. Now, a mast and a hub are both internal components in the system. The nacelle will rotate 90 degrees, giving you vertical landing and flight capabilities. And then it rotates back down into this orientation, allowing you to fly like an airplane. So I used to crew them. I used to kind of fly in the back, and I used to work on them. So that's why I have interest and kind of give you a little bit more understanding of what's going on when I'm saying like prop rotor or hub. This is a prop rotor. It connects all your blades to it. Um, or your blades get connected to it, excuse me. And then earlier I mentioned I was interested in the interaction between the hub and the mast. So the hub is a component of the prop rotor system. Uh, can't really see it here, but it's buried beneath all the stuff that gets kind of bolted to it and connected to it. Uh, Something to note of that is the hub has a tapered section and a splined section. The splined section connects, and so does a tapered section, connect to your mast. Tapered section kind of carries all the weight from the hub, and the spline section is what's transferring all that torque being generated from your engine. Now, the engine is located down here below this prop rotor gearbox. It's connected down here, spins some gears, the gears, then rotate your prop rotor mast, which then via your spline interface with your hub spins the prop rotor, generating thrust and allowing the aircraft to fly. Pretty neat. So that's some background and what's inspired my project. Now, I decided to model everything axisymmetrically. One allowed me to do it 2D. Two, it kind of lets me take advantage of not needing to use so many nodes. To model all that would be massive. So even just doing the hub and the mast, which because I kind of can roughly to scale based off memory, based off some pictures, and just my experience with them, I kind of backed out a rough shape and rough dimension of what this interface would look like. So this is the hub. The hub I'm using in aluminum for. This is not what you would find in that aircraft, but it's a great substitution. Didn't know the hub uses a composite material, and I wasn't super familiar with applying that material in Abacus or Wheeler to get in information on like layering. So aluminum was a great substitution. It's used in other hubs in rotary aircraft. And then for the mast, I'm using an alloy steel. Again, that's something else that's very commonly used in mast design. It might not be what's used in the Osprey, but this is just kind of a rough analysis, and it's super good enough to get me where I'm going for this study. Now, what I'm actually studying uh, is the interaction between the hub and the mast, specifically in the tapered section. So when I say tapered section, I mean this taper right here, this slant. And I'm interested in the contact pressure between the two parts and what that contact pressure does. So that contact pressure generates a hoop stress. That hoop stress is going to uh, be applied from a mast nut. Now, a mast nut is threaded all the way around. Now, imagine this is 3D, right? It goes all the way around, one big circle on to your mast until it sits flush with the top of the mast and is also kind of applying light pressure to the hub. So the mast nut itself doesn't get direct torque applied to it. It doesn't get the preload applied to it. It gives you the means to apply the preload though. The mast nut has 12 through holes drilled into it in its center all the way around that allow you to install a bolt. Now the bolt is about 3/8 inch in diameter, and it gets torqued to about roughly 22 foot-pounds per bolt. So there's 12 of them total. Now I'm working in metric. Backing that out, how I did this is I took the torque equation, and then I solved for the compressive force needed to achieve that torque. So doing it that way, and multiplying that number by 12, you get 170, about 170 kilonewtons of force being applied from the mast nut into your hub. And that's what I'm modeling here in this preload reference point. And that's what I use it for. So back up a little bit and give you an idea what I mean when I'm saying what these parts look like. Bring this guy up here real quick. Zoom in. Sorry about that. Got my scaling all off. But yeah, so this is axisymmetric, so it's going to rotate about this axis here. Model. Yeah, just rough dimensions. This is all metric, right? So this is going to be like 2.5 inches in diameter, I want to say. That's going to be half inch-ish. Or no, an inch. That's an inch. Yeah, that's a half inch. And this is about 9 inches here. I chose to go in metric, mainly for material properties. I just find it easier that I find that approach to be easier, so that's what I did. So I'm gonna exit out of this guy, back on out. Yes, it's okay. All right, so I did the same thing for the mast, also axisymmetric. A section for each material for each component. And then in my assembly, I have the hub and the mast. I chose not to model in the mast nut, kind of to save one more part from needing to be meshed. And I figured using a reference point would be a great substitution and a good approach to do this. It's going to mimic the interaction that I'm going after between the three parts. So my steps, I have just initial and the preload. That's it. It's a static general. That's all I'm doing here. Nothing too crazy. And my interactions, so I have my hub to my mast right here in that contact length that I'm interested in this analysis. So it's a hard contact, and that's all that's holding my hub on. Just like in reality, that's what's holding the hub on. So it's a great way to kind of mimic what's going to be seen in life, real life. So again, that's my hub to mast, and then my constraint manager, I have a thrust here, which I currently have turned off, and we're going to talk about that a little bit later. But it was after I got everything working, I was just kind of curious to see what thrust would do, so I added it on in. And then I have my connecting my preload to my hub, which I already talked about. That is a hard coupling. Hard contact, excuse me. It's coupling, it's a hard contact. These are all coupling as well. So looking at my loads here, briefly kind of talked about them. I have it on right now. It's going to turn thrust off. We have my preload up here at the top, and we have the thrust. And then for my boundary conditions, I just have one at the base, and all it is doing is constraining me, or the faster way to look at it, in my Y. That's it. In reality, the mass is going to be installed in proper order. It's going to be pressed in to a bearing, and it's going to allow it to rotate. But to keep it simple, we're just using a constraint down there to keep this thing from falling when you apply that preload. So my mesh, since I'm using an axisymmetric model, I'm kind of limited on what I can do for the most part. Oops, wrong one. So I'm choosing to do a quadratic because it can give you a more thorough calculation of what the behavior is. I mean, you're going to have 8 points to go off of versus 4 if I did it linear. And then it's a quadratic, right? So I'm just going to get higher resolution. And then it's going to enable me to use less nodes, right? So that's great. And that's why I chose to go that route. Just going to run it. Turn that back off. So as I mentioned, I am interested in hoop stress. It's S33. So I'm seeing the behavior I would expect. My preload is going to apply a hoop stress into my mass, and that what that's going to do is going to be it's going to be in tension, and that's what we're seeing here, right? That's the behavior we're seeing here in our table. And then our left, we're going to anticipate this to be in compression. That's exactly what we're seeing here. So a way to think about this is I'm applying a force here at the top. So if you take like a water bottle, an empty water bottle, lie on its side, or even, if you're strong enough in vertical orientation, you press on this empty water bottle. Now it's going to want to expand in a radial direction. And that's the same thing you're going to see here when you press down on the top. It's going to want to expand in a radial direction. That's a behavior we're seeing. And on top of that radial tension from the hoop stress is going to apply that compression in the mass, and that's what we're seeing. That's a reaction coming from these stresses being applied into your hub, generating that hoop stress, that tension hoop stress is giving you a compression in your mast. And that's really cool to see that behavior, kind of what you're anticipating. And just to give you an idea of how much this thing moves just by installing it, not a lot. I mean, that's basically nothing. This is in meters, so that's what 0.001 meters, like not a whole lot. So 1.5 millimeters. I don't know why I said it that way in the first place, but it's 0.5 millimeters. Yeah, pretty cool. This thing doesn't move. You're not going to see it. All right, so this kind of got me thinking, what if I put a thrust on it? How is it going to behave? Is it going to be any different? So that's what we're going to do next. And I kind of turned that on because I think it makes it easier to understand what's going on here. Again, these things are hollow to allow cabling to come up. You have sensors, you have de-icing systems, everything needs to kind of be monitored. So that's what that's for. And that's why they're hollow. It's pretty cool. So let's go turn that thrust on. Now, the way I came about this thrust is the max takeoff for an Osprey is about it is 60,500, or at least it was when I was in it. It's been quite some time. These numbers could have changed. And that is for a rolling takeoff. So meaning you would never take off vertically with that much weight. But in my analysis, that's exactly what we're looking at, is how much stress would be present if we took off vertically at 60,500 pounds. So in order to do that, you're going to be using 135 kilonewtons of thrust per side, right? So each side of the Osprey kind of splits up that weight. So our hoop stress really doesn't change a heck of a lot, right? Yeah, all right. And our vernices also is well within, for the mast itself. The mast itself is well within its yield strength. The hub is yielding, but again, this is in a scenario you would never see it, and it's with material that actually isn't used on the aircraft, and the dimensions are ballpark. So for me personally, warm and fuzzy. Even I've flown on these aircraft, so that doesn't bother me at all. Um, and I would anticipate that not using the same material, same dimensions, you're going to see slightly different behavior, right? That makes sense. So your hoop stress, still seeing the same behavior, right? You're getting tension in your hub and you're getting compression in your mast. And that's going to be present throughout the flight of the aircraft, no matter what it's going through. The mechanical stresses it's going to be imparting. You're going to see very similar behavior in this interaction, in this coupling. And it's super cool. It's super cool to see. It was a really fun project. Took a little bit more thought to set up. I know it looks super straight up, but like how I was going to approach modeling it, how I was going to back out the stresses I wanted to see, and how to like kind of check those, right? So I had a lot of fun. Hope this is somewhat helpful and kind of gives you an understanding of an axisymmetric analysis and why they are helpful and useful. They kind of greatly simplify design to keep you from having to have these crazy big 3D assemblies with thousands of nodes, hundreds of thousand nodes probably for something of this size. Um, yeah, and still give you the information that you're chasing and you need to make a decision or to get an understanding of a behavior that you're seeing. So if you like, please subscribe. Just kidding. But no, seriously, I really enjoyed this class. So yeah, thank you.